Hello everybody, this is the Exam 2 review. My name is Holden. Okay, first off, I'm going to go over the chapters on the test. It is as follows: 4, 6, 7, 8, and 9. Let's jump right into scatter plots and correlation. Is this a positive or a negative association? Well, we can clearly see it's positive because of the clear upward trend. And same goes for this one, except it's opposite. We can see a clear negative trend, so it is a negative association. What is correlation? Correlation measures strength. There are two ways to find the correlation in R. You can do correlation data $X, comma data $Y, or the converse. The reason why is because correlation in R is a symmetrical property, so you can find it both ways. Here are some conditions for correlation. First is the quantitative variables condition. It wouldn't quite make sense to find a correlation for categorical variables. Next is linearity. The variables must be roughly linearly related in order for the correlation to matter, and there must be no outliers. The last one, between -1 and 1, isn't a condition so much as it is a characteristic of correlation. That is, the correlations are always going to be between -1 and 1. The magnitude or absolute value represents the strength, so a correlation of -1 is just as strong as a correlation of 1. And the sign just represents the association. So negative means negative association. So let's look at this real quick. Do you see anything wrong with the graph? Are there any conditions that look like they're being violated, assuming the variables are quantitatively related? Yes, there is. Direct your attention to the bottom right. As we can see, there is an outlier. This really messes up the correlation. And to prove this, I calculated the correlation with and without that point. With the point, it's 0.6. Without it, the correlation is 0.96. So keep outliers in mind. Next is R squared. You find R squared when you find the correlation for your model and then square it. The meaning of R squared is it's the percentage of variation in Y explained by the regression of Y on X. What does this actually mean? To understand better, let's look at an example. Let's say we are looking at a factory and we're measuring the amount of workers in a factory and the cells for the factory. Workers are the X variable and cells are the Y. R squared in this scenario would be the percentage of variation in cells explained by the regression of cells on people working in the factory. Next, let's try to make it a bit more systematic by going through solving a linear model problem. First, you need to check the conditions. The quantitative variable conditions should be checked as it is with correlation for the same reasoning. It doesn't make sense to make a linear model if the variables are not quantitative. Next are the linearity and outliers condition. You can check both of these with the scatter plots. The R commands right here are the R commands to make the scatter plot, so you can check these conditions. The first makes the model, the second creates the plot, and the third makes the AB line. The AB line is the line of best fit created from the least squares regression that shows up in the graph right here. Now, the outlier is still there, but this is what you would do if there were no outliers present. Next is the equal spread condition, which you check with the residual plot. The equal spread condition is also called the homoscedasticity condition. Let's find out how to check the equal spread condition. To make your residual plot, you use these commands. The first line makes the model. The second line creates a vector for the residuals of the model. The third line is plotting the X variable against the residuals. And the fourth line is creating an AB line at 0, 0. This is the residual plot. And this is what you need to check for the equal spread. The things specifically for which you look out are patterns. We do not want any patterns present. Certain patterns tell us specific things about the data. A fan or cone-shaped pattern tells us that the prediction of Y is less accurate at large numbers. If there is a fan or cone present, it violates the equal spread condition. If there is any curvature in the residual plot, it violates the linearity condition. Ideally, the residuals look random. What is a residual, though? What are these values on the residual plot? Well, residuals are the observed minus predicted values. Observed values are what you're measuring in the real world. they will be present in the data set. Predicted values are the values that you predict with your model. You get these by using the coefficients and putting it into y equals mx plus b format, but I'll go over that in a few moments. The other important thing about residuals is that whenever R is making the line of best fit, we're doing a least squares regression. A least squares regression is one that minimizes the sum of the squared residuals. The sum of squared residuals is taking each residual point, squaring them, and then adding them together. How do you go about linear model problems? First, after the conditions, you make the model. Once you type in model as shown in the line of R, you will get something that looks like this. It gives you your intercept, which is right under where R says intercept in parentheses, and it gives you your x value. The equation is y equals slope times x plus intercept. As I mentioned earlier, it's y equals mx plus b format. So if we actually wrote it, it would be y equals 0.8905 x plus the intercept, 8.2297. What does this mean in practical terms? The interpretation of this is very important, beyond just getting the numbers. It would mean that with an increase of x by 1, y will increase by 0.8905. So to spell it out even more, let's go back to our previous factory example. Since people working in the factory is the x variable, it would mean if you increase the workers by 1, the cells will increase by 0.8905, whatever units you're doing. Now we've covered scatter plots and correlation, let's go into random variables. A random variable is a variable that takes on different numerical values with different probabilities. We've divided it into discrete versus continuous variables. Discrete random variables are variables for which you can list the possible values, and continuous random variables can take on any value in an interval. Let's go over some examples. SAT scores are discrete. The reason is because they can only be between a certain range, and in increments of 10. You can't score a 12.15 or a 12.10.5 or anything like that. Next, foot size. Foot size is continuous. Your foot can be any size. However, this begs the question of shoe size, which is discrete. Shoe size is discrete because there are only set shoe sizes. Amount of rain is continuous because it can rain any amount, and then height is also continuous. There's a spectrum for these things. The mean of a random variable is the expected value. It is the weighted sum of all possible values. Let's go over an example. Let's say the probability of something being 0 is 40%, the probability of it being 1 is 40%, and the probability of it being 2 is 20%. What is the expected value? You would use the R code I put on the slide. You would first create a vector for the probabilities, a vector for the values, and then sum the product of these two vectors, and then that is your expected value. What is R actually doing though? Well, R is multiplying the 0.4 times 0, the 0.4 times 1, and the 0.2 times 2, and then adding all of these together. So it's important to conceptually understand what it's doing and not just think you're putting in random things and telling R to do it for you. To find the standard deviation, you do the first steps and then you continue like this with the following vectors I created here. But they must be independent to do this. Keep that in mind. So here's a summary. You should put this on your exam sheet. You don't want to miss any problems like this. And there are two things you might be asked, most likely, the expected value or the mean and the standard deviation. This could also be asked in a different format. The way these would be worded is the expected value of whatever x is plus whatever y is, or ex minus y, and you would just add the means of x plus y, or the difference of x minus y for these. Next, for standard deviation x plus y or standard deviation x minus y, you would add this. You would take the square root of the sum of standard deviation x squared plus the standard deviation of y squared. But they must be independent to do this still. Please keep that in mind as it's very important. Next, let's go into the normal distribution. So we've talked about this plot, the normal distribution plot, quite a lot, but you also need to know the paranormal distribution. You don't actually, that's not on the test. This plot is the distribution of probability for continuous variables, and it can be drawn with this curve, also called the probability density function. However, there are a few departures from normality for which you cannot use this graph. Those departures are multimodality, skewness, and outliers. An example of multimodality, because I think it's the hardest to understand out of these three, are that if we took something like height theta and we looked at it, there would be a female mode and a male mode because each has a different mean. And other than that, it's pretty simplistic. For skewness, it should be fairly symmetrical. It doesn't need to be perfectly symmetrical, but you should be able to tell. It will look fairly symmetrical. And next is outliers. Again, you do not want there to be extreme values. Next, the 68, 95, 99.7 rule. It's just talking about how 68% of values are within one standard deviation, 95% are within two, and 99.7% are within three standard deviations. So the chance that you find something outside of three standard deviations is very rare. Next, let's go into the p-norm function. The format of p-norm is q, mean, and standard deviation. The important difference between it and q-norm is it returns probability. If it's standardized, the mean is 0 and the standard deviation is 1. So if you have anything standardized, you can just put in p-norm, whatever it is, because 0 and 1 will be assumed, but you can type them out if you would like. P-norm finds the area to the left, so I would encourage you to always draw a picture to ensure that you're finding the correct area and you don't actually need to do 1 minus p-norm to find the area to the right. Q-norm is similar except it returns values instead of probability, but it's a similar format for which you put it in. The example I have here is if you want to find the cutoff for the top 10% of something, you use Q-norm 0.9, mean, and standard deviation. The reason why is because top 10% cutoff is 0.9. You should just look at this example until you really understand why you use 0.9 here so you don't get tricked by anything like this. As you may have noticed from the homework, when calculating standard deviation to use in p-norm, you may use two different formulas. You could use square root p times q divided by n, which would find your standard deviation as a proportion, or square root p times q times n, which finds standard deviation of a number. There are good examples on the practice test of this for you to understand better, but we'll go through an example to try to make it more clear. There's a coin that has landed on heads 210 out of 350 times, 60%. What is the probability of getting at least 210 out of 350 with a fair coin? Here's one way to do it, where we would use square root p times q times n to find the standard deviation, which is 9.35. Notice that we're using 210, which is what we're looking at, 175, the expected value or the mean, gotten from 0.5 times 350, and the standard deviation as a number. We couldn't do this if we couldn't find the standard deviation this way if we were using 0.6 for the value we're looking at and 0.5 for the mean. But if we find the standard deviation with square root p times q divided by n, you can use 0.6, 0.5, and then the standard deviation that way. Both of these will give you the same answer. So think about when you would use each and the type of wording that would be used. Here are some conditions for using the normal model. The sample size condition, success failure, independence, 10% condition, and randomization. The sample size condition says n must be large enough. Success failure condition says that the number of successes must be at least 10, and the number of failures must be at least 10. And you can calculate this by multiplying n by p and n by q, or n times 1 minus p. The independence condition means that the sampled values are independent. The 10% is if there are no replacement, n must be less than 10% of the population. And the randomization condition is that you need to randomize data. So if we were doing some type of pharmaceutical clinical trial, for the randomization condition to be fulfilled, we would need to assign subjects randomly to treatment. Finally, let's go into the sampling and confidence intervals section of this presentation. I have some important definitions here, and it's really important to just know all of these. And at the end, we'll go through an example to tie some of them together. But for the most part, you just need to memorize these, and not only memorize the definitions, but also conceptually understand why we're even doing all of this and what the point of statistics is. Sampling error, not an actual error, sample-to-sample differences. Sampling distribution is the distribution of proportions over many independent samples from the same population. Again, I would recommend doing the end of chapter problems because some of them incorporate these definitions and what to look out for. Population is the entire group of individuals about whom we want information. This should be contrasted with a sample, which is described by statistics instead of a parameter. And a sample is a part of the population that we examine to gather information. A census attempts to gather information from every member of the population. This definition is fairly intuitive because there are things such as the US Census, which tries to gather information about every household in the United States. Let's look at this application question that I made. I'll give you a few moments to read through it, or you can pause and read through it. Okay, so now I'll go over it. You can pause the video if you haven't fully read it and try to identify what all of these numbers mean yourself in regard to which definition they apply to. And then I'm going to go over them right now. So 1500 is the sampling frame because we have 1500 numbers that from which we are randomly calling. 300 is the sample. I'd like to point out that I specifically worded it this way because 500 are chosen, but only 300 answer. So those 500 aren't the sample because they didn't answer the phone, so we can't ask our survey question. Austin residents are the population because we're attempting to find out what the preferences of people in Austin are in regard to your OU. We want the information about them. P-hat is 99, or 0.99. And P is unknown. So this is important because we're using P-hat to estimate P. If we already had P, it wouldn't make any sense to do a survey to try to investigate this type of issue. This is similar. The purpose of samples is to estimate things about the population, and we would estimate several things. So one is P. P-hat is a statistic from a sample, whereas P is a parameter that describes a population. And as I mentioned, we're using P-hat to estimate P. Similarly, we're using standard error to estimate standard deviation, as I've worded it here. And what standard error actually is the sampling standard deviation. So a binomial is a sum of Bernoulli trials, and here are the conditions: fixed number of independent trials, same probability of success, and I would like to note you do not need a certain sample size for this. The margin of error is an amount interval extends on either side of the estimate. Below, I've included the R command for how to find it. You can literally type in exactly what I have, as long as above you set confidence level equal to something, set P-hat equal to something, and set N equal to something, and then you can just run all these lines and it will give you your margin of error, which is very nice. However, I've included the equation for margin of error for a particular reason. I want us to look at the relationships, because you might be asked something similar to the homework where something is happening with your confidence level and we want to know how it affects the margin of error or how it affects the interval in regard to wider or narrower or anything of that sort. So let's walk through it. We increase the confidence level. What does that affect? Well, as we can see here, it affects the critical value. A higher confidence level means a higher critical value for Z-star. So that would mean the margin of error increases with increased confidence. Increased margin of error means the confidence interval is wider. Walk through a few of these examples yourself, and then see if you can figure it out in various circumstances and really test yourself about it. It's an important relationship to understand. Also, the relationship between N and the margin of error. We'll go through that now, though. There's an inverse square relationship between sample size and margin of error. This means to decrease the margin of error by 2, we need to increase sample size by 4. So the inverse part of the relationship means to increase one, we have to decrease the other. So we're trying to decrease margin of error by increasing sample size. So if you truly understand, you can answer the question on the last bullet point. By how much would you need to increase sample size to decrease margin of error by 4x? Well, since it's an inverse square relationship, you know if you're decreasing margin of error, you need to increase sample size. So we need to increase sample size by whatever 4 squared is, 16. Here are the calculations for sample size. You can just type what I have and then also include the top box of R, so you don't have to go and mess with the formula. You can just create vectors and then R will do it for you, which is really nice. But there's something very important to remember. Very, very important. Round up. Round up. Seriously, round up. There's no reason to miss the questions because you rounded down. Even if it's 35.1, the necessary sample size is 36. Even if it's 0.01. The reason why is because if you round down, your margin of error is going to be slightly too high, and that really matters. Confidence intervals. So the important thing to point out here is you will have access to the R help pages on the test. The ci.prop is from chapter 9. So you could just copy and paste it from the R help pages, or it may be built into the test file you download. Either way, you do not need to put the really long ci.prop function creation on your exam sheet. You just need to know how to use the ci.prop function, which is, as I've included on this slide, you need the p at in and conf.level, which it defaults at 0.95, so really you could leave off conf.level equals 0.95, but if you change the confidence level to 0.9, you do need to include that part. I cannot emphasize enough how important it is to know what the confidence interval actually means. It's very easy to calculate it with R because we just put it in a very simplistic format like this. But by doing so, we often preclude the possibility of us actually being able to interpret it. So it's very important to go back into the content and make sure you conceptually understand the confidence interval. And I've included 2 correct applications of what the confidence interval means. I encourage you to look back at your homework to try to conjure up what they mean without looking at the answers, and then you can look at them to see if you truly understand. But essentially it means not that you are whatever percentage confident that the true percentage falls on the confidence interval. Feel free to email me if you have questions. There will also be a TA-led exam review on Monday where they go over the practice test. But I hope this video was helpful. Please reach out to me. I'm Holden. My email is on the syllabus, holdenarcher1@gmail.com if you have questions, and I hope this was helpful. Good luck studying. You can all do it.